Hello everyone, myself Matam Sahana, MSc at Physics, studying in Regional Institute of Education, Mysuru. Today I'll discuss about symmetry of main symmetric phases. The objectives are introduction about liquid crystals, and you'll know about symmetric phases, symmetries found in symmetric phases, and explanation of symmetry in symmetric A, symmetric B, symmetric C, and symmetric F. Comparison between symmetric phases regarding tilt and positional order. And last one is visual representation of molecular arrangements within symmetric layers. So first we'll see about liquid crystals. Liquid crystals. The characteristic orientational order of the liquid crystal state is between the traditional solid and liquid phases, and this is the origin of the term mesogenic state, used synonymously with liquid crystals. As you are seeing in the diagram here, solid arrangement of molecules of solid is given and liquid is given, and the liquid crystal is the intermediate arrangement of between solids and liquids. And liquid crystal materials generally have several common characteristics. Among those are a rod-like molecular structure, rigidness of the long axis, and strong dipole or easily polarizable substances. So this is about the liquid crystals. Now we will see characteristics of liquid crystals, which parameters describe the liquid crystalline structures, that are orientational order, positional order, and bond orientational order. In orientational order, measure of the tendency of the molecules to align along the director on a long range basis. In positional order, the extent of which the position of an average molecule or group of molecules show translational symmetry. Bond orientational order describes a line joining the centers of the nearest neighbor molecules without requiring a regular spacing along that line. So this is about the characteristics of liquid crystals. And then some of the applications of liquid crystals are, there are many and there are still being discovered, and few of the applications are liquid crystal displays, liquid crystal thermometers, and optical imaging. So this is the introduction about liquid crystals. Now we will see about the symmetric phases. Symmetric. The word symmetric originates from the Latin word symmetricus, meaning a soap-like texture. So it will have a texture of soap. The symmetric liquid crystals have positional order along with one long range directional order. Since the layer structure is well defined, any molecular tilt or distribution inside this layer structure is distinct to each other. And symmetric phases can be characterized by its periodicity in one direction of space, and its point group symmetry. There are many types of symmetric phases. There are symmetric A, symmetric B, and so on, which further we'll discuss about that. And in this symmetric phase, like in this phase can be reached at lower temperatures than the nematic phase. Here you can see the arrangement of molecules in the symmetric phase also. And not all positional order is destroyed when a crystal melts to form a symmetric liquid crystal. So this is about the symmetric phase. And main symmetric phases, like other liquid crystal phases, exhibit various levels of symmetry. Here are some common symmetries found in main symmetric phases. The common symmetries are polar symmetry, layer symmetry, translational symmetry, chiral symmetry, and hexagonal symmetry. In polar symmetry, some main symmetric phases have a polar symmetry where the molecules have a net dipole moment. This can lead to interesting electric optic properties. And layer symmetry. In symmetric phases, molecules are arranged in layers The layers can have different symmetries, such different symmetries such as being parallel or tilted with respect to each other. This is regarding layer symmetry. Now we'll see translational symmetry. Symmetric phases are characterized by long-range translational order within the layers. This means that the molecules are arranged in a periodic pattern along one or more directions within the layer. Now it's chiral symmetry. Chirality can also play a role in symmetric phases, leading to chiral symmetric phases with specific twisting patterns. Now it's hexagonal symmetry. Some symmetric phases exhibit hexagonal symmetry within the layers where the molecules arrange themselves in the hexagonal symmetry. This is the small topic about the symmetric phases. Now we will see types of symmetric phases. In symmetric phases, which are a type of liquid crystal phase, symmetry plays a crucial role in understanding their properties. Symmetric phases are characterized by layers of molecules that are arranged in a ordered fashion. Now first we will see about the symmetric A phase. In symmetric A phase, the molecules are arranged in layers with no positional order within the layers. However, the orientation of the molecules within each layer is same. This phase exhibits a one-dimensional long-range order. Orientation of molecules affect symmetric A properties. And in symmetric A, the molecules are arranged in layers with a specific orientation within each layer. This molecular orientation impacts several key points in symmetric A, that are viscosity, optical properties, response of external fields, and phase transitions. First, we will see about the viscosity. The orientation of the molecules affects the flow properties of symmetric A. The ordered alignment within the layers can lead to different viscosities along different layers directions, influencing the flow behavior of the phase. So this order alignment within the layers can lead to different viscosities and optical properties. The orientation of molecules in symmetric A can impact its optical properties such as birefringence and response of external fields. The orientation of molecules in symmetric A makes it sensitive to external fields like electric and magnetic fields. Change in the molecular alignment due to these fields can alter the properties of symmetric A, making it useful in various applications like displays and sensors. And the last one is phase transition. The orientation of the molecules can also affect the phase transition. Changes in temperature or external condition can lead to reorientation of the molecules, resulting in phase transition in phase transitions to other liquid crystal phases. We have seen about the symmetric A. Now we will see about the symmetric B. In this phase, molecules exhibit a tilted arrangement within the layers. In symmetric A, there was no tilt. Here there is a tilted arrangement within the layers. Unlike the vertical alignment in symmetric A, this tilt introduces a different symmetry compared to symmetric A. These molecules in the symmetric B have tilt with respect to the layer normal, leading to a distinct molecular organization and symmetry properties. This tilt creates a different type of long-range order within the layers, affecting the phase's overall symmetry characteristics. So this is about the symmetric B. And symmetric F. This is not much important, but we'll just know what is symmetric F. Symmetric F phase is characterized by a ferroelectric ordering of the molecules within the layers. This phase exhibits spontaneous polarization perpendicular to the layers. So this is regarding the symmetric B and symmetric F. Now we will see the most important phase, that is symmetric C. This symmetric phase is similar to symmetric A but with tilted molecules. The molecules in the symmetric phase have a tilt with respect to the layer normal, giving rise to the chiral structure. This phase is also known as chiral phase. The molecules in the symmetric C exhibit a tilt that adds an extra level of complexity of the symmetric properties of this phase. This tilt in symmetric C refers to the angle at which the molecules are oriented relative to the layer normal. Now, the tilt in symmetric C affects the symmetry in several ways, that is chirality, helical structure and optical properties. This helical chirality is the tilt of molecules in symmetric C introduces chirality into the structure, meaning that the phase lacks mirror symmetry. And in helical structure, the tilted arrangement of the molecules in the symmetric C can lead to a helical structure within the layers. And optical properties, this tilt in the symmetric C affects the optical properties of the phase, leading to phenomena like optical rotation. This optical activity is a consequence of chiral symmetry induced by the tilt of molecules. So this is regarding symmetric C. Now, so we have finished different type of symmetrics, that is symmetric A, symmetric B, symmetric C and symmetric F. Now we will see comparison between different phases regarding tilt and positional order. We have seen differently. Now we will just compare between the different phases. That is, in symmetric A, molecules are positional in layers with high positional order, meaning they are well organized in parallel layers. However, there is no tilt order present as the molecules do not tilt with respect to the layer normal. As I already said, in symmetric A, there is no tilt present in between the layers or molecules. And in symmetric B, there is both positional order with molecules organized in layers and tilt order, where the molecules tilt within the layers. This combination of positional and tilt order distinguishes from symmetric B to symmetric A. So, symmetric B has both positional order and tilt in the molecules, whereas symmetric A is not having. And in symmetric C, it is similar to symmetric B. There is positional order with molecules arranged in layers, but in addition, there is tilt order where the molecules tilt or rotate within the layers. This tilt order along with the position order contributes to the unique properties of symmetric C, such as it responses to the external fields. This is the comparison between the different phases. As we already studied all this, it's just an points taken from the different phases. And this until now we have studied in definition. This is a visual representation of the molecular arrangement within symmetric layers. So first picture is the symmetric A phase and the second picture is the symmetric C phase. So now where is the symmetric B phase picture? So that is given as assignment for you people, that you will have to find it out. So this is, yeah, here you can see in symmetric A phase molecules are arranged parallel to each other in vertical. Here in symmetric C they are tilted as we already saw it. So this is regarding visual representation of molecular arrangements. Now, regarding symmetric phases, we have all understood. We will see some of the applications of symmetric phases. Symmetric phases such as symmetric A, symmetric B, symmetric C have various applications in liquid crystal technology and other fields. Some common applications include display technology, optical devices, sensors, smart windows, and biomedical application. Like what will come under display technology, we will see. Symmetric liquid crystals are used in display technologies like LCDs, like liquid crystal displays for devices such as this liquid crystal displays can be present in like our daily life uses like televisions, computers, monitors, and smartphones. This is regarding display technology. And the second one is optical devices. These optical devices are like optical switches, tunable lenses, and variable optical attenuators. The ability of symmetric phase to change their molecular orientation and respond to external stimuli allows for the manipulation of light transmission and polarization, making them valuable in optical systems. So this is regarding optical devices. And sensors. Sensors applications includes temperature sensors, pressure sensors, chemical sensors. The sensitivity of Smectic phases to external factors enables development of responsive and accurate sensing devices. And smart windows. Smectic liquid crystals are employed in smart window technology for controlling light transmission and heat insulation in buildings and vehicles. By adjusting the alignment of liquid crystal molecules in symmetric phases, smart windows can dynamically regulate light and heat entering a space. And the last application is biomedical applications. Symmetric liquid crystals have potential application in drug delivery systems, biosensors, and biomedical imaging. So this is all regarding the symmetry of in main symmetric phases. Hope you have all understood it. Thank you.